Hello. So for our presentation, we're going to talk about varnished silver next. Uh, so I and Pierre Nicolas, next please. Uh, I and Nicolas had to work on a problem. The problem is pretty straightforward. You have a silver, and we worked with a company that wanted it to be micro-perforated and lacked to protect it. But what we saw was that the silver gets yellowish, and the company doesn't want that. So we wanted to see if there is any physical explanation and if we can propose a solution to fix it. Next.
So basically, first we use this model that was not micro-perforated, with what just a layer of Zappen. So we use a cubed car modem from 1954, adapted for transparent and specular materials. So basically, what we have is that when the rays are reflected on the silver, it gets yellowish due to the Zappen. So with that, we add micro perforations. So basically, there are holes which are 300 nanometer depth, and we use for simplification the incidence angle was normal, and also we have a second modelization, which was an enhancement of the hole, which was 5 micrometer depth, and also there was not only silver but two different metal, because between the left and the right there was an enhance of luminance, which was not expected. So that's why we use this model. So what we obtain is that if we look at the blue curve, it was the silver by itself. The red curve was the silver with only a Zappen on it and no micro perforation. So we saw that we have the reflectance is it's a bit less on the blue than on the red, so that explains the yellow color. And also, we can see that if we add micro perforations on 300 nanometers hole depth, we obtain the green curve. And if we use the 5 micrometers layers with different metals, we can see that we have an enhancement of luminance, and also we can see that the yellow effect is still enhanced due to that curve. We see that the difference between the green and the purple curve is smaller on the blue than on the red. So we modify the model, and we use that the Zappens have a certain transmittance with, for example, pigments, and so we try to find this T in order to have the absorption coefficient of the pigment.
So we have one objective is to get the new transmittance with pigments, for example. How do we get this transmittance? We had to look at the LAB model. So it's a color model that's the state of the art. And we wanted to fix the B component, which is the opposition between yellow and blue, and get a set of solution that would make the spectrum give the wanted yellow. There is a trade-off to do because you can't gain luminance, but you have an array of solution that can give you a different spectral reflectances. And as you can see, it's shifted down for the whole spectrum. Next. As you can see, here are some results that we've got. So there is a comparison with the final model. You can see that it's a bit darker, but because the human eye is more sensitive to color, it's better, and that's what our clients could have if they choose like that's the brightest solution. Next. As you can see, we have like the absorption coefficient should be less on the blue part, which is normal because we no should be yes, which is normal because we want to be less yellow. Next.
So basically, we obtain that we have a set of solutions in order to have the curve behind the one which have the right B star value. We use a statistical model of microperforation in order to model those, because there was no anything that we can rely on, and also that we see that we can find a certainty, and hence and so a certain concentration of pigments in order to have the right color, but it costs luminance. So
thank you for your attention.
Yeah, if you have questions, you can ask us.
Okay, thank you.